On a hot day or during a long workout, what's your favorite drink to cool down? It may vary depending on the person, but as I understand it, the best option is always good old water. And if you like your water cold, like my husband Ryan, you might put some ice cubes in there. Both liquid water and solid ice water are made of the same chemical, water, and have the same chemical structure, H2O or dihydrogen monoxide. They're completely different in appearance and in physical properties. Why is that? Well, it's because these two forms of water are different states of matter. The state is the form in which a piece of matter exists. There are 4 states of matter: solid, liquid, gas, and plasma. And we will talk about the first 3 in this course because those are the ones we see in the study of fibers and dyes. It turns out that for each state, the arrangement of atoms within the matter determines its physical properties. Let's take a look at these arrangements and properties and start with solids. In solids, we have individual particles packed up against each other like this. The particles look like a lattice and are as well packed together as oranges in a crate. The characteristics of solids come from how these atoms are arranged. Solids are rigid and have a fixed volume and shape, which comes from the fact that the particles in a solid are unable to move past each other. Solids are not compressible due to the lack of space between the individual particles. And finally, solids do not flow because of the lack of mobility of their particles. In the periodic table, most elements are solids. We see them in groups 1 and 2, all of groups 3 to 12 except for mercury, and then most of groups 13 to 14. The same is true for rare earth metals. Next, let's draw out what the particles of a liquid look like. Liquids take the shape of their container, but not the volume. This is because particles can slide past each other to a much greater degree than solids can. Despite this mobility, liquids are not compressible because there's not a whole lot of room between the molecules still, even though they are more mobile. And another consequence of the ability for water particles to move past each other, liquid particles, is that liquids flow easily. There are 2 elements in the periodic table that occur naturally at room temperature as liquids, and these are mercury and bromine. That brings us to gases. If we were to draw out what gas particles look like, we draw a few and then a lot of space between them and little arrows indicating that these particles are moving around rapidly. Gases take up both the shape and volume of the container due to the rapid movement. Unlike solids and liquids, gases are compressible, so think of a gas tank that a scuba diver would take down with them on a dive, precisely because there is so much space between these particles. Finally, for the same reasons as liquids, gases flow easily because the particles are able to move past each other. On the periodic table, we find gases at the top, so hydrogen and helium, in groups 17 and 18, and then some of the nonmetals and the pnictogens and chalcogens as well. So oxygen and nitrogen, for instance, occur naturally as gases. Now, we're going to go into more detail about another way we classify matter, whether a particular element is a metal, a non-metal, or somewhere in between, aka metalloids. Metals are shiny and they conduct electricity. They are malleable, which means they can be hammered, and ductile, which means they can be stretched into wires. Most are solids at room temperature, except mercury, and they tend to be very shiny. And some examples of these metals are the metals that we typically associate with jewelry, such as silver and gold and platinum. Generally, there's a lot of overlap with the solid category and the metal category on the periodic table. We find metals in groups 1 to 12, the rare earths, and then some of the solids in the lower parts of groups 13 to 17 are metals. For group 1 and 2, a commonality of all metals is that they have a tendency to lose electrons to become cations in a predictable pattern. For group 1 and 2, electrons are lost from the s orbital, whereas in the d block, electrons can be lost from both the s and d orbitals to form positively charged cations. Now, on to nonmetals. Nonmetals are poor conductors of electricity, are not ductile and malleable, are not shiny, and generally are found in either the solid or the gas state. Some common examples are the gases that make up air, such as oxygen and nitrogen, and diamonds. Generally, we find nonmetals on the upper right-hand side of the periodic table, in groups 14 to 18 specifically. Generally, we find metals on the right-hand side of the periodic table, in groups 14 to 18. Nitrogen, oxygen, fluorine, sulfur, most of the halogens, and all of the noble gases, as well as carbon, are nonmetals. A commonality among nonmetals, with the exception of noble gases in group 18, is that they all want to gain electrons to become anions. Then finally, there's the intermediate category of the metalloids. Metalloids have some characteristics of both, but are generally solid. Metalloids are known as semiconductors and are used a lot in technology. For instance, silicon is used in computer chips, and this is where the silicon in Silicon Valley comes from. Boron, silicon, germanium, astatine, antimony, and tellurium are all metalloids. Metalloids can either gain or lose electrons, which is part of why they have properties of both, but we generally do not see them form free ions.